Well, it was about almost 10 years ago now when we heard persistent memory is coming, and it's going to be byte addressable. It'll be memory semantics, but it'll be persistent. And actually, there had been some products shipping, so this actually did start even before that. And I drew put a picture in the upper right there where you can see NVDIMM-N, which you can still purchase today from some vendors, where there's DRAM on the DIMM, but it squirrels away the contents on a power failure. They're pretty small, and when I looked at this, all access was through a driver, so they were really just treated like storage. So if we go on to the next slide, we knew that we wanted to treat persistent memory like memory, to really exploit what we could do. But in order to do that, we knew we needed to have a way to find it, to give persistent memory blobs a name, and to figure out whether you had permission to open up the persistent memory. How do you back up persistent memory? How do you manage it? How do you change permissions and so on? So we decided that we needed a programming model that specified all that. And you can see a little cartoon of the programming model in the upper right part of this slide. And we talked to a zillion software vendors. We talked to a lot of people who were going to make persistent memory. And we wanted to make sure we came up with a standard programming model that didn't mean you had to lock into one vendor's private API. So, it was an interesting task for me as an Intel employee, because I wasn't going to then make an Intel branded API. I was going to make instead something that was just for the ecosystem. So we headed to the SNIA, the Storage Networking Industry Association, and if we go on to the next slide there, kind of show a timeline here of what we did. It was, 8 years ago now, we formed the Non-Volatile Memory Programming Technical Work Group in SNIA, and we had immediate participation from a lot of people, including operating system vendors like Microsoft and Red Hat and big companies, ISVs like Oracle, and VMware was there. It really was incredibly popular. And we came up with the programming model and published it in January 2013. By July in 2013, I had created the first repo full of programming examples, and they're still out there. You can look at them, but they seem kind of silly now because we were really just starting. And then we finally published the official Rev 1 in 2014. So actually, it's quite a while ago now, and it's pretty mature now. In fact, it's been shipping in multiple operating systems for a number of years now, including Windows and Linux and VMware. Okay, let's go on to the next slide. So we had a programming model. So then what did we do after that? The programming model tells you how to get to persistent memory if you're an application. How do I open it? How do I map it into my address space so I can use it like memory? But if you just stop there, it's like telling somebody, here's a pointer to 3 terabytes. Have fun. It's not very friendly to a programmer because, it makes the programmer manage everything. So we started stepping back and thinking, what could we do to make persistent memory programming easier? And this was the beginning of the Persistent Memory Development Kit. We went around and we talked to programmers, and all of them basically came up with the same top priorities. We need a way of tracking which persistent memory is allocated, which is free, kind of like malloc, like a C programmer would use, or like GNU, like a Java programmer would use, but persistent memory aware. And we need to make a way to make transactions so that if the program crashes or the machine crashes, the data structure is still kept in a consistent state. And finally, we need some common containers like lists and queues and hash tables and so on, so that everybody doesn't have to develop these persistent memory data structures themselves. So that was really the motivation behind making the Persistent Memory Development Kit. If you go to the next slide, you can see what the first thing that everybody tried back then, which is just to make a version of malloc, the C allocator, that's persistent memory aware. And you can almost immediately see why it doesn't work on the left, is because there aren't enough arguments to malloc. If you allocate persistent memory, but before you actually link anything to that allocation, your program crashes. You not only have a memory leak, you have a persistent memory leak. It's going to be still leaked even after the program restarts. So we came up with this API on the right, which was our first try, and that's in that Linux examples repo on GitHub if you're interested in looking at it. But it was simple, and it got some of the ideas out there. Then we built this team, this Persistent Memory Development Kit team, and we got some bigger brains involved. And Piotr, who's about to talk, is the brain behind all of the libpmem obj logic, where we really handled generic transactions, and it's a very powerful library. So I'm going to turn it right over to him and let him take it from there and take you through it. Go ahead, Piotr.
Thanks, Andy. So with that, let's now see what directions and goals we used to actually develop the PMDK based on the history that Andy just talked about. So, but before we consider actual solutions that we developed with PMDK, let's focus on the underlying principle that our software really has to use. So we actually have to solve real problems. And so in the case of PMDK, we want to solve real problems using persistent memory. And the solution part of that statement is actually not that hard. Well, it's hard, but it's manageable. And there are difficulties actually coming up with what problems are actually applicable to be solved with persistent memory. So to consider how to do that and what are those problems, we look at persistent memory in 3 different ways. We look at PMEM as memory because it is byte addressable memory, but at the same time it's affordable and bigger than DRAM, which enables previously impossible use cases, multi-terabyte heterogeneous memory systems. So we are going to be talking about that later on a little bit. Next, we look at persistent memory as storage because it's actually non-volatile, right? So this allows us to have systems with extremely low latency, gets and writes, stores and writes, which allows us to do very, very unique things. But, however, the most interesting part begins when we consider persistent memory as both memory and storage. And that's where the difficulty starts. We have to look at problems that are traditionally solved using algorithms that were either designed for memory or were designed for storage. And now with persistent memory, we have to step outside of the box, so to say, because we have to first identify the real problems, not the problems that storage has, or not the problems that memory has, but the actual underlying problem. And once we identify that problem, we want to solve that using the best possible abstraction. So let's walk through those views on persistent memory one by one. So the first view of memory, persistent memory as memory, is that, like we said, persistent memory is bigger, but it's more affordable than DRAM, but at the same time, it is a little bit slower. So once we attach persistent memory into a system, that system becomes heterogeneous, which means that applications can no longer assume that all memory is the same, which is the status quo of today. But even if you don't have PMEM, you might already have a heterogeneous memory system. For example, if you have a multi-socket system where memory from remote socket has actually different characteristics. So the operating system tries as hard as it can to actually blur those differences and still try to present the unified view to the application, but applications can get best results if they actually are aware of the hardware they are running on and then adopt correctly to the memory that is available. And with PMDK, one of our goals is to hide existing applications, use persistent memory or in general heterogeneous memory systems in an efficient way by intelligently and scalably managing memory placement. When we look at persistent memory at storage, we now have to consider what does that change when it comes to writing data. And the biggest difference is that we now have an extremely fast latency, access latency, but the other dimension is that we can write in cache lines, which allows us to do things like reducing write amplification. But the disruption that persistent memory causes in the storage hierarchy is not unprecedented. When SSDs first became available, they caused a similar disruption, maybe with the exception of the store granularity. And the techniques that were developed for SSDs are still valid today. So all of the DM caches and techniques like that are still very much viable for persistent memory. So another aspect of PMEM that is often forgotten is that persistent memory is byte addressable, also as storage. So if your application already takes advantage of memory mapped I/O, then using DAX, which stands for direct access, we no longer have to worry about the page cache, and thus allowing us to reduce costs by just not using page cache, because we can just access data directly. So second goal of PMDK is to aid modification of existing applications to transparently take advantage of persistent memory in storage solutions. And now the most interesting bit, when we consider persistent memory as both storage and memory, we have to think bigger. So one of the ideas that I had on my mind when I was working on PMDK is that persistent memory, when you consider it as just flat storage hierarchy with just persistent memory, it effectively invalidates the computer science field of database storage design. But when you really think about it a little bit deeper, then you can't just discard all of that work, because persistent memory is not, it doesn't stand alone. Persistent memory is still has to be used with other types of memory and storages, right? So what PMEM really is just another tier. So not only doesn't it invalidate database storage design as a study field, it actually makes it harder, because you no longer have to think about only memory and only storage and how to blur the difference between those. You also have to think about how do we tier memory between tier data between memory, PMEM, and storage. And that really, when you actually realize that, it unlocks a plethora of different problems that were solved in different ways with storage for databases, and now can be solved in a completely different, reimagined way with PMEM. So one of the things that are really stand out, at least to me, is that PMEM can really allow you to reduce access latency to data, because even if your data is in storage, if you have a traditional database model, you can access it directly. You don't have a heavyweight cache miss from the page cache that you will have, and you just can't read directly. But it also reduces write amplification, because if you have a transaction that is smaller than a page, which is very common, then you no longer have to either write the entire page or buffer it in DRAM and lose consistency of a transaction, but you can just write it directly. And if you do that using using non-temporal stores, you can just do it with one mem copy, and the transaction will be consistent, which is very cool. So the third goal of PMDK is to allow usage of novel techniques to solve the problems that arise when you consider PMEM as memory and storage. So in addition to those three main goals, we also have to consider durability, consistency, reliability, and performance, because those 4 things are very critical for us. And I listed those things in order of importance to us, because when you have something that is performant and only superficially appear to work, then that solution isn't really that useful, because you can't rely on it to actually work when it actually matters. But not only is it not useful, and when you use a solution that superficially appears to work, then it can actively harm you when something bad happens. Right? So our focus in PMDK is to make sure that everything we do and that our algorithms and data structure are very reliable and always provide consistency. And on top of that, as of today, our PMDK data structure actually provide you synchronous consistency, which is in contrast to many databases today. And that is actually in part enabled by the fact that persistent memories has small write amplification factor. So in PMDK, we run literally thousands of tests every single release and hundreds of tests every single commit to make sure that everything stays safe. But at the same time, we do not neglect performance. And on the chart that you see on the slide, you can see the improvements we've made since our 1.0 release. And actually, it was actually surprising to me when we looked at those numbers that we actually improved performance by over 5 times over the course of a couple of years. And we did that by looking at by reimagining our concepts of what is memory and how to use memory, right? With the view of so a general direction and goal that we have, and we had from the beginning, was to make persistent memory programming easy. And when I think about that, then I come to the conclusion that not everything can be easy. There are some things that are simply difficult, and to make them flexible, the abstraction that we have to come up with isn't always going to be easy to use, because then we will be trading off performance for convenience, which is fine, but we want to make sure that efficient things are possible. So I do like the quote from Larry Wall, who is the author of the Perl programming language, that says that we should make easy things easy and hard things possible. So that is the exact same principle that we try to follow in PMDK. And we do that by layering our solutions into small building blocks. And we are going to be talking about that right now. So let's take a look at what is PMDK and what we have delivered so far. So as I talked about on the previous slide, we have a stacked variety of solutions. So at the very bottom, we have our low-level primitives that are fairly difficult to use, but not really, that provide you with the greatest flexibility that you can have. So those are the libpmem and librpmem. We also have some libraries that allow you to use persistent memory as just memory, and those are mankind and bmcache. Those are kind of their own separate thing. So on top of those low-level libraries, we provide more complex libraries like libpmlog, libpmj, and libpmlog. So the most prominent of those libraries is libpmj, which is what Andy talked about in his last slide. So this is the realization of his ideas that he had at the beginning. So libpmj provides you with the memory allocated transactions and all those really crucial things that you need to write persistent memory programs. And on top of that, we actually layer more stuff. because we realized that libpmj and the interface it provides isn't really that simple to use. It's easy, but simplicity is in the eye of the beholder. So we realized and had feedback that we needed to make something different. So we created bindings to C++, Java, and other languages, and specifically in libpmj C++, our C++ binding, we developed various containers and data structures that actually make the system programming far easier. But that's not where we ended up with. We actually laid one other block on top of that, which is PMKV. And PMKV provides you with a very simple key value store interface that takes advantage of all of the work throughout the stack that I just described. And obviously, this is all built on the programming model that Andy described at the beginning. So with all those different solutions, it actually might be hard to figure out when should you use which thing. And so let's go over those things one by one and see how those things can be used. And when we do that, we have to also look at how much effort you will need to actually use that solution and how much you can gain. So it's kind of like by using the easiest solutions, you can gain the least. But that's how this graph is on, but that might not necessarily be 100% true. So, so for example, with memory mode, which isn't really a part of PMDK, memory mode is just a different mode that you can use the Intel Optane CPU system more with. And it exposes PMEM as just memory. And it tries to make the assumption that our memory is the same true. And you can just use this using malloc. You don't have to modify any of your applications. And on this chart, on the chart that we just saw, it's shown as the least amount of effort because that's true, but also the least amount of gain, which is not that 100% true. Memory mode can actually be utilized fairly well if your working set fits in the DRAM that you have in your system, but also if your application is not particularly latency sensitive. So as with everything, the gain you can get from a solution will depend on your actual workload. So my standing recommendation is to usually just measure and use the simplest possible solution that you can use, and then measure if you do actually need to move to the next step and use the more difficult solution. Okay, so the next solution that we provide is libmemkind. And with libmemkind, we use persistent memory as memory. So we do not take advantage of its persistence. And when we think about what that means, it means that applications now have two separate tiers of memory. They have DRAM in their system and they have PMEM in their system. And that creates a need to have two separate memory heaps. And libmemkind is exactly that. It gives you a memory heap for your PMEM. And but not also only PMEM, but also other types of memory, like HBM. So the next solution that we have is libvm cache, and it also uses persistent memory as memory. It's a fairly simple solution that provides you a get-put kind of an interface with an LRU replacement policy. And this interface was created by the need of having a performant and scalable solution that didn't use the existing libmemkind because of fragmentation concerns. So libvm cache was created as a solution to inefficiency problems that you might have when you create very large heaps and allocate and cache objects with wide variety of different sizes. So next we have PMKV, and PMKV is our key value store with a very simple interface. So PMKV is primarily written in C++, and it exposes a very convenient interface for that language, but we also port to PMKV, create bindings, official bindings for PMKV for different languages like Python and Java. And so the next step is libpmj, and this is where things get complicated, because all of the previous solutions were fairly simple and similar to things that people use today. With libpmj, we kind of diverge from that model and come up with novel techniques. So libpmj provides you with transactions and allocations, like we just said, and it does so in my opinion, fairly simple way. libpmj is available in C, so that's the primary language it is written in, but we also provide C++ bindings that make everything much more convenient. So in the example that you can see on the slide, we insert a new element into our linked list. And when you discard the transaction closure, this kind of looks like a normal volatile application. The only difference is the transaction, obviously, and make persistent. So make persistent is the memory allocation that you do, which is modeled after make shared or make unique from C++ standard. And so this fits fairly well, and it can be used to modify even existing applications that want to use persistent memory. And finally, we have libpmem, which is the lowest level library that we provide in PMDK. With libpmem, all you are really given is a way to map a file, a persistent memory file, a way to tell if that file is actual persistent memory, which is the ispmem variable on the example, and a way to transfer data between pmem and DRAM in a way that is efficient. So this library is really just a convenience for the low-level primitives exposed by the operating system. So that was the look over all of the solutions that we have, most of the solutions that we have in PMDK. And like I said, when I started going through this chart, my recommendation is actually to start at the very beginning of this chart with memory mode or with memcached, and then see if that solution is good enough for your problem. If it isn't, then you can move forward to the other solutions. Because at the end of the day, what matters is if the solution, the problem is solved, not if it's perfect and ideal. So in addition to the libraries that we just discussed, we also provide various different utilities and tools to make programming easier and manage persistent memory. So I'm not going to go over all of those tools, but the important thing to notice here is that there are multiple different ways of accomplishing different things with persistent memory, and the most important part is to have the ability to actually manage your memory and then try to benchmark your memory, so benchmark your applications that you actually did with persistent memory, and debug and profile those applications. And the debug tools that we created were mostly created for our own need in PMDK, but we also try to generalize them so that they are useful for everyone. For performance, all of the existing tools that you will use for performing the work, and the VT amplifier from Intel is actually a great tool to see and observe behavior applications that use persistent memory. Okay, with that, let's take a look at what we are going to do next. So remember when I introduced libpmem? Well, we decided that it's time for a new version of libpmem, and we call that libpmem2. So we had, libpmem was the very first library that we created. And it had a lot of crust. We initially created it only for Linux, and that caused some problems with the abstraction that we have. And that abstraction also wasn't flexible enough to introduce new functionality that we needed for RAS, which stands for recoverability, availability, and serviceability. So things like bulk bug detection or unsafe shadow count detection. And libpmem also isn't very flexible when it comes to allowing you to map a file. It has one single API that forces you into a certain path. So with libpmem, we want to address all of those problems and give the user a very flexible API that can read everything that is required. Another problem that we see and we see users actually struggle with is concurrent programming. And when I say concurrent programming, I mean both just using logs and mutexes for your data structures and algorithms, but also when you want to use log-free programming, so atomic. Because with pmem, things are not so simple, and you have to consider the difference between visibility. So when things are visible from other threads, and persistence. So when things are actually persistent on the storage media. And your application shouldn't make a decision on another thread on data that isn't actually persistent. So that problem with visibility versus persistence is very difficult to solve. So we took it on ourselves to address that problem and introduce both low-level semantics that will simplify concurrent programming, and we want to do a kind of scalable API in PMJ that will make log-free programming easier. And with C++, in C++, we want to introduce ready-made containers that are concurrent, scalable, and just work fairly well in applications. And then the user doesn't have to actually worry about all of the different problems with logs and atomics. So, and finally, since remember when I told you that PMTV is built upon libpmj in C++? So in PMTV, we actually take advantage of all of the work that we've done for libpmj C++ and create engines for PMKV that directly and out of the box support scalable operations. So even today, right now, when you go on PMKV, you will see that it supports scalable operations. And finally, let's talk about heterogeneous memory systems. So a little bit ago, I showed you an example from Mankind. And that example, if you paid attention, actually allocated memory directly from pmem. It clearly had a hard-coded pmem variable. But does that really matter? Does it matter to the application that it's actually allocating from persistent memory, even though it's not going to take advantage of its persistence? Well, I don't think it does. And what we really need to do is to create an interface that allows the user to convey its intentions with regards to the memory that it's going to use. So kind of like memory traits. You want to allocate memory that, for example, you want to allocate memory that is fast or you want to allocate a memory that you have a lot of. So instead of saying allocate from PMEM, your application should say, for example, allocate this this object in fast memory, or allocate this object in some capacity tier in my system. And a good example for that is a binary tree, a B+ tree, where you want to have very fast access to your indexing structure, but the leaves and the actual values in a B+ tree, which will be accessed less frequently, can actually be allocated on the capacity tier in the system. So in that example, you will allocate your keys with a hint that those objects should be fast, and then you will allocate your values, leaf nodes, with tag hint that this should be allocated from maybe slower but more memory of which you have bigger, so a capacity. And ideally, we should also make it so that all applications simply scale from systems that have one, that are homogeneous, which means that they have only one type of memory in the system, which will then make such an interface just fall back to allocating interior, to multi-node heterogeneous systems, which might have DRAM, PMEM, HBM, and all of that on 8 different sockets. Right? So creating such an interface is challenging. So the example that you see on the screen isn't a real example. This is not the interface. It's unlikely that this is the interface that we will actually publish. So this is kind of a call to action. So if you have any ideas how this problem can be solved and how to design that interface, we would love to hear your feedback. Yes, call to action. I forgot I had this slide. So let's to reiterate, the goal of PMDK and the goal that underscores everything is solving real problems using persistent memory. And we can only come up with so many ideas. So if you guys have any real problems that persistent memory can help solve, then we would love to hear about that. And since persistent memory and PMDK is an open source project, I encourage you to just go out there, go to our website and create a GitHub issue, or write to us on our mailing list and describe your problem, and we will be very happy to learn about that problem and then try to come up with solutions that will be then integrated into PMDK and help everyone. But we also think that persistent memory in general presents a very unique and interesting research challenge. And so remember when I said at the beginning about invalidating the field of computer science of database storage engine design? Well, like I said, persistent memory only makes things harder. So we spend a lot of our time just thinking about different problems that we can solve using PMEM. And again, we can only come up with so many ideas. So if you have any ideas for research work, we would also like to hear about that. So and finally, if you just want to play around with PMDK as we showed you, then you can get started today. And if you don't have any elaborate hardware platforms, that's also fine. The system can be emulated on normal PCs. In fact, I developed most of my code on PMEM, and I just tested on my desktop and just tested on a server PMEM. So if you just want to play around, you can get started today. And obviously, our website has a very nice domain, pm.io, so it's easy to remember. Okay, so the last slide. So we recently have written a book that describes the content of this talk in a much bigger detail, and also describes the problems that we solved using the programming model, describes all of the solutions that are available, and also describes those solutions in detail. So if you are interested to learn how we, for example, validate or test our software, and you can learn that in our book. The book is available freely online. Okay, so that was our presentation. Thank you very much.